basically said, you know, the hammer toe is not optimal. Yeah, the bunion's okay.
Good evening, everyone.
It's just not optimal.
Welcome back to some of our regulars of 3 years ago, and welcome to those who are here for the first time. We're really glad to be back in person. My name is Mike Sullivan. I'm the External Affairs Manager here at Skidaway Institute, and we're very fortunate to have a couple of visitors from our main campus in Athens with us this evening. I would mention one thing. I had a couple who said, "Oh, I didn't hear about this." One of our main ways of disseminating the schedule, and we don't have a full schedule yet. That's just a matter of logistics of trying to get everybody to get us the right information. But we have an email list. We promise we're not going to spam you. We do everything we can not to do that. But if you're not getting our emails and you'd like to get notice of events like this and the whole schedule, we've got a sign-up sheet right here. Just be very careful when you do your email that it's easily legible, because a J and an I can look an awfully lot alike on a piece of paper, but of course they're completely different. When you're pressing a key on a keyboard. So if you'd like to mention that. I'd like to introduce our speakers this evening. Dr. Ervan Garrison is a professor of anthropology and geology at the University of Georgia. Received his bachelor's and master's degrees from University of Arkansas and a PhD from the University of Missouri. He served 2 stints as the head of the Department of Anthropology at UGA. He's done extensive archaeological and anthropological work here on the Georgia coast, including right here on the Skidaway campus, back in the woods that you came through on the way here. And then Dr. Kelly Cronin is a conservation paleobiologist, and she can explain what that is. Well, she studies chemistry and the growth of bivalves like clams, scallops, and oysters in order to understand ancient environments. Dr. Cronin received her undergraduate degree in biology from Cornell University and completed her master's in geology at the University of North Carolina, Wilmington, and then got her doctorate at the University of Georgia in 2020. Dr. Cronin and Dr. Garrison, you're on.
Thank you.
Thanks very much for coming. The announcements. Today we are going to be talking about underwater road cuts and what they can tell us about past environments out on the Georgia Shelf. So I want you to cast your mind back to Earth about 21,000 years ago. Oh, I have to turn, I can't indicate with the laser up here and y'all can't see it. So about 21,000 years ago was at a time period called the last glacial maximum, meaning that this was the most recent time on Earth that glaciers were at their maximum extent. You'll notice some, okay, thank you. How's that? No. It is on. If I pull it right up to my mouth, that doesn't work either. Okay, I think the microphone might be for YouTube. Yes, okay. So I will do my best to project. If in the back you can't hear me, just raise your hands and I'll bear that in mind. All right, so 21,000 years ago, glaciers were at their the most recent maximum extent. You'll notice this white part here is where we think the glaciers were at about 21,000 years ago, covering most of the northern hemisphere, covering North America well down into the Midwest. And a more subtle consequence of this on the global map is the coastlines are just a little bit different than we expect them to be now. It's easiest to see in Florida. Check out how much green is sitting over Florida. All of that land was exposed because all of that seawater was locked up in the glaciers. Also at 21,000 years ago, the fauna or the animals living in Georgia, very different from what we're familiar with now. We had, I'm sure squirrel relatives were here 21,000 years ago, but in addition, we had things like the giant ground sloth, a huge bison with great big tusks, and mammoths. And here's a zoom in on what we thought the sea level looked like, not 21,000 years ago, but about 18,000 years ago, when sea level was still very low because glaciers were still very big. And this is what we're familiar with now. If you check out the green over the gray here, this is the modern coastline. We think that this gray was all exposed as that all outside of, so not underwater anymore, as that about 18,000 years ago, as that water was locked up in the glaciers. If you looked east out of this building now, it would be 100 miles before you saw the edge of the ocean. We might as well live in Alabama at that point. And just to show you how dramatic sea level change was, all right, good, this is going. This is the modern coast of Florida as sea level, as the glaciers retreated, started to melt, and sea level started to rise, starting at about 14,000 years ago and headed toward the present. If you pay attention to this top right-hand corner, you'll start to see at about 3,000 years, the modern coastline of Georgia emerge. And Florida is starting to look a little bit more familiar as we go forward in time. There's Lake Okeechobee, finally. So for paleoecologists and for archaeologists that are interested in the landscape and the animals that were present in Georgia during and just after the last glacial maximum, we have a bit of a problem. All of our evidence is currently underwater because as those glaciers retreated, as the ice melted, sea level rose, and where we are now on the modern coastline that would have been 100 miles inland 18,000 years ago, all of the things we're interested in is buried under water and then a layer of sediment. Geologists have ways of solving this problem to see the ancient past. Does anybody have any academic or casual relationship to geology in this room? Casual's fine. If maybe you're familiar with roadcuts. This is a real way that real geologists do actual geology. Up here on the road cut, where you see this grass, is the modern topography, the modern land. But when humans blast away rock to make roads and buildings, they often leave us these lovely walls that we can sample and see gradationally down into time, into the past. Now, the underwater road cuts are neither this neat nor this time resolved, but we are trying to use a similar idea to get at the environments of the past under the modern Georgia, under the ocean off the coast of Georgia. And what we're using are things called scour nuclei. So let me break that down. Whoops. This is a cylinder sitting in a sediment tank with current running over it, and the current will be going from right to left. When you put an impediment in front of a current, the current is going to flow over this impediment and scour the sediment away behind it. So this bar is nucleating, is the nucleus of this scour, the sediment getting blown away. And what you're seeing here is not necessarily the surface of the sand, but the sand underneath. Now, this is an idealized version of this in a flow tank, but we can see it in real life as well. Right here, we have a shipwreck underwater. Here's the ship. And you can see this gigantic scour nucleus. They call the area near the boat the moat, or near the impediment the moat. And this broader area of scour is called the comet, so you can think of it like a comet's tail. The amount of sediment that gets blown away, that scour site, is proportional to the size of the thing blocking the sediment. So when we are looking for these places to find these underwater road cuts, these scour sites, we're looking for great big things. And handily, Georgia helped us out here without even knowing they were going to. Georgia sunk over the last several decades a bunch of vessels to make artificial reefs. But if they are situated properly to the tidal current or to the prevailing currents in the ocean, they are nucleating scour behind them. And these are the sites that we are looking for to find evidence of that past environment. So for the rest of this talk, we're going to ask why we care about this, which I hope I've already given you a clue into. Why does NSF care about this? Because we did need money to go look at these things. What have we found, and what are our plans for the future?
Hi, I'm Irv. This is a tag team between Dr. Cronin and myself. Thank you very much. Okay, why do we care? Well, we're scientists and we are interested in sometimes arcane things. We want to know more about this recent past of maybe the last 18, 20,000 years. And as Kelly has told you, it's all underwater. And once you get to the seafloor, it's covered with basically a modern sand sheet. So we've got to move that sand sheet out of the way. So as she's described for you, we use these obstructions that create scour to just do some dirt moving for us. And it moves quite a bit of sediment. So it will help us look into the past like these road cuts do. And there's quite a past out there. These are things that we already have found. I think this is a recognizable extinct animal. This would be the woolly mammoth, and this happens to be a tooth that was found near Gray's Reef National Marine Sanctuary, and we actually found this bone. I can't read the blurry numbers, but I think it's 2001 that we found it. And this is a cast. This is a cast that we made of a bone from right here on this bison, and it's broken here because when we did the radiocarbon dating, the lab wanted more of the bone than we wanted to give, so we only gave this much of it. You have to bend, go with the flow. Again, as Kelly showed you, our coastline was a whole lot further east. And so this is just a snapshot at 11, and maybe it's not 100 miles offshore, but it's probably a good 50 or 60 miles offshore. And then as the glacier starts to melt, starts to retreat, the shoreline starts to retreat back to where it's recognizably closer to what you and I would say is Sapelo and Cumberland and Wausau. So, but at 7,000 years ago, it's not there yet. These, again, come from Gray's Reef National Marine Sanctuary. These are hard-fought artifacts. You find one about every 2 or 3 years of diving out there, and it's cause for celebration. Okay, this one's beat up simply because, again, you have to sacrifice things to get information, and the only way we could identify the material that this projectile point was made from was to take a section, polish it, put it under a petrographic microscope, and decide, okay, now we know what this stuff is. But when you reconstruct it and you put the tip back on it, it looks pretty much like a Christmas tree, and it is a verifiable projectile point from about 8,000 years ago. So maybe we can put Gray's Reef a little bit closer here to the shoreline. And this is just, this is your scraper that if you're scraping cheese or scraping carrots, whatever, that's all that thing does. But to us, it's humble but very important. It says, Humans were here. So why does, and it's FCARE, National Science Foundation. All of the money that comes from NSF comes from us. Okay, we've all contributed our tax dollar. National Science Foundation distributes this money to probably 30% of the proposals that it gets every year. The attempt, well, let me put it this way. All federal agencies are charged with surveying and inventorying their land holding or seafloor holdings, which would be NOAA and Bureau of Ocean Energy Management. You're supposed to identify and protect these resources because they belong to, again, they belong to us. The ability to locate and characterize these sites is difficult. Why? They're buried. Okay? And they're composed not like shipwrecks, which can be iron or wood, sometimes are quite dramatic, stand above the seafloor. Prehistoric sites tend to be stone, bone, wood, and shell. And when you really look at them up close, they look exactly like the seafloor. So they're very, very hard to find. What these agencies had done, they had invested a lot of money, sometimes up to 7 figures, to attempt to use a methodology where they would core the seafloor. They would then take and split the cores back in the laboratory. They would take a sample every 10 centimeters. They would do dates on them. They would look at any inclusions in them. But when you think about it, and I've thought about this, the 2 studies that I mentioned to you collected about 100 vibrocores, and these are just 3-inch, basically they're 3-inch irrigation pipes, okay? And they're about 19 or 20 feet long. We won't even guess how many millions of square acres are on the continental shelf. We totaled it up. The amount of sediments and sample that came from those vibrocores worked out to about, I think, 80 shovel tests. Now think about that. So your methodology is working. It's very difficult to do this. So NSF said, have you got a better idea? Yeah. Let's use these scour nuclei and these erosion to see if we can open up larger areas of this buried landscape and see if we can see something. All right, so what did they do? They funded us in the middle of a pandemic. We actually got started in the fall of 2020 and working with the Skidaway Institute of Oceanography and specifically Michael Robinson, we started taking data at what we call the northern tier. These are reef SAV, reef KC, CCA, JY, and KTB. DUA and CAT didn't have any of these large obstructions, so we ignored them. But we have looked at 7 of these artificial reef sites over the last 2 years, and we're presenting that information to you right now. This is what Mike did. Actually, I helped on this. I watched. Well, he's quite a guru with his instrument, and this is his instrument. It's an interferometric side scan sonar that hangs off the side of the RV Jack Blanton. And all of the electronics are up here on a shelf, and that's where Mike and I were. But what it does is it takes a fairly good snapshot of the seafloor. So, okay, this is the artificial reef CCA, and it's an old 200-foot barge. We take this, and again, in the beginning of the pandemic, we spent a lot more time looking at data on computers than we did actually going offshore for obvious reasons. And so what we do is we take the raw data and we wash it through software. This is geographic information system software. And all you're seeing here are two different colors. You're seeing blue and you're seeing green. Green is a modern seafloor. It's a beach. There's nothing there. You see the blue, this is where the currents have been busy. And they have carved out these moats and comets, if you will, around this old barge. And if you come in, what we do is we can then lay a cross section across this in the software, and then we can look at the cross section in profile, and this is the seafloor. Then as you approach the structure, see what happens? You get a moat. Then you go on the other side of it, and you not only get a moat, but look at the difference in elevation. That's 2 meters. So this thing is over 7 feet deep, and it extends significantly away from this thing. So this is where the comet is forming. And then we really go crazy. No, I want to give a shout out to this young woman. I want to say this. Some of our UGA undergraduates are some of the brightest kids you'll ever meet in your life. This is Andy Anderson. Everything you see here, Andy did. I again watched. And again, you see, now you can see in the background the underpinning to this. That's that side scan sonar. But then we start to play with that and say, well, what's the depth? Okay, well, here's that sand sheet. And then as you approach this obstruction, look at all of this stuff here. This has been eroded away. And we've quantified it. We put numbers with it. So we know then this is probably a good place for us to go looking for evidence. And so we put together an Excel sheet. You're supposed to do that. But where you see the yellow is these are specific targets that we say we've got to go to these places. And we have. So what have we found? Keep going. All right. There we go. We do a lot of this. Cue the robot. All right. This is the robot. Okay. We opted to use technology rather than putting divers in the water every time we went out there. And in fact, we were exploring this technology. The underwater technology has really taken some great leap forwards in the last 20 years. And it's become approachable in price. I think this little beast probably doesn't cost more than $15,000 or $16,000 with all the stuff we've hung on it. It'll shake your hand. Oops, excuse me. It's got a gripper. You'll see the gripper in a minute. It's got all the kinds of lights that you need. It's got a 4K camera, which doesn't happen to be on there, and it's got a sonar hanging off the back of it. But we can put this little guy in the water. It's got an HD camera up here, and we can turn it loose, and it doesn't complain. It doesn't come back and eat a lunch. And so we kind of like the robot. So long as the battery is working, it's fine. Then we bring it back and we put a new battery in it. Okay? So what have we found? Let's see. We're going on a dive. This was, and you can see the gripper? Okay. Sitting right under the camera. We're just drifting down to the seafloor through a not very inquisitive group of barracuda. And you can see in the background our target, which is an old dredge that the Corps of Engineers gave to DNR, and DNR took it out and sank it. So we're trying to land as close to this thing as possible, and you can see the moat, can't you? Mm-hmm. We make hard landings. I make hard landings. My other pilots, they don't do this. Those two young women, well, they grew up with Xboxes, right? Okay. Right. That's my excuse. So anyway, but you can see that sand. Look how loose that stuff is. It's remarkable. Now, I'm going to let this play. Nothing happens fast on the bottom of the ocean. For one thing, you have to get your bearings. You have to make sure that the video is on. You have to make sure that the notebook is open and somebody's writing this stuff down. So there's a lot going on while the vehicle is just sitting there. And you keep an eye on the monitors thinking, okay, there goes the Barracuda. But I want you to watch the Barracuda. You got them? You notice that? Did you see that? There's a reason for that. It's coming. There they go. There they're back. But they'll take off again. If you look at this stuff long enough, you can meditate. And we can break these things, we can break this video down frame by frame by frame, and you can spend hours staring at this stuff trying to find something. But there's a lot of information in that video right there. But again, let's just wait just a few more minutes, not even a few more minutes. Look, there he comes. Hi there. Yeah. If you've never seen a sand tiger, that's a sand tiger. So now, it didn't scare the robot at all. The operators talked about it. Did you see that? So yes, again, now we can move. Okay, and again, we can find our target, and we can drive over to the target. And you only have to put up with this for about another minute and a half, so bear with me. But again, we're headed, this horizon is the edge of that moat. So what we've got to do is we've got to take the vehicle over to the edge, and then we've got to go down into that moat and see what the erosion has exposed. So that's really all that's going on here. And I think it's over. There it is. You see how deep that is? Turn off the thrusters. That's good. Now everybody can see. So they're taking the vehicle into the, look how big that thing is. All right. All right, Dr. Cronin.
So along with the robot, we have been taking ponograbs of the samples of this ponograbs of the sediment under the water. And what this involves is John Bitchy or me or one of the undergrads throwing this ponograb over the side after setting it with a pin. Once it hits the bottom, this snaps shut and grabs whatever sediment is at the bottom and whatever else is there. And these are the sediment that we use, or the sediment that we collect is what we use to try and figure out the paleo environment, along with any information we get off the robot. So we have to take it back to the lab. We have a lovely, relaxing boat ride back to the lab. And then we have to sort the sediment. So first we have to dry it. It came out of the bottom of the ocean. It comes up wet. And somewhere between 2 and 24 hours in the drying ovens at the geology office or at the geology building, get it all nice and dry for us. And then we drop it into the top sieve on this stack of sieves. And a very loud 10 minutes later, the undergraduates and I go back and we lock ourselves in the office so we can hear ourselves think while this thing's going. Although I have to say it's better than doing it by hand. What this does is it's a graduated set of sieves where the largest screen size is the top. The screen sizes get progressively smaller. So what we have at the end of 10 minutes is a sorted sediment sample where all of the big stuff, primarily shells, is sitting at the top, and all of the smaller stuff filters out into the various sizes of sand and silt. We and once we finish that, we weigh each section, and then we feed it into an Excel sheet program called Gratistat that tells us what kind of sediment we have. Spoiler alert: it's almost all medium sand. It just depends upon how much shell material we picked up with it. That changes the amount of the very big stuff that we have. We go through, or I mean, I say we, but what I mean is one of our fabulous undergrads, Kelsey Williams, goes through these videos basically frame by frame, and she knows what's interesting and where we need to find the edges of our scour and other things that we need to see and consider going back to look at. In with the sediment, we have been looking for pollen, and we have been successful. If you want to get a lot of information very quickly about the plants in an area, looking at a sample of the pollen in that area is a good way to do it. And we luckily have pollen in our samples, which is surprising because it comes from underwater, but we do have it. These are some pictures of pollen from our samples. Kelsey Williams, the same woman that does that goes frame by frame, also somehow has the patience to prepare and examine pollen slides. These are some samples from the pollen slides that she brought back from USGS. You can see some good pine pollen here, some broken pieces of pine. We seem at this point to have mostly trees in our pollen, but we have a lot of slides to look through. We've been trying a more experimental technique for this kind of work, also looking at the environmental DNA. So traditionally, when you're looking at DNA samples, you think about taking a blood sample from a human and trying to match it to some other human to find relationships with. But this is a relatively new technique where instead of trying to match individual DNA samples, you are getting all of the DNA in the sample, and they just say, here's all the species we think you have. Just everything in the environment. This has been, we have some ongoing issues with this. This is, of course, a very sensitive process. And the first sample we got done got reported back in October. It was all grasses, liverworts, and like a little freshwater amoeba, which tells me that sample was contaminated. There was no marine DNA in it at all. Same thing happened when we sent out the second one. But in that one, I made sure that we tucked in a little polychaete worm that came up with our sample. So no, I'm not sure what's going on with the environmental DNA. We have when we have plans so that we have some plans for the future for another trip on the boat. We are going to refine our sampling technique a little bit so we don't get as much contamination in our sample. If anybody knows anything about this and wants to talk to us later, please do. We could use some advice here. The thesis statement for what we've found with the bivalves is that we're looking at a mix of past and present environments, which is exactly what we expected to see in an underwater road cut. So that's good news. First, I'll get to the radiocarbon dates in a second. First, I just did a quick visual identification of the bivalves we had pulled up from some of the samples. And what I was looking for were things that didn't belong. We're 20 or 30 miles out when we sampled these sites. So what I'm expecting are relatively deep water offshore mollusks. And I found some of those. We found a Tectonatica that I think came up alive. It's a little snail that definitely belongs in that environment so far offshore. But we also pulled up a bunch of surf clams and oysters. And those are distinctly shoreline species, which means that what we were finding were bivalves that were there where we sampled was the shoreline, not when it was 30 miles out. When we pulled, a very exciting thing I found was oysters that had been stained black, which suggests that not just they were shoreline, but they were actually sitting in the marsh when they were alive or after they died. So we're looking at potentially like Barrier Island rollover of this area. And I picked some of the oysters out, particularly some of the black oysters, to get them radiocarbon dated to see what we were looking at. We have, again, found some interesting mixes of past and present past and present organisms in these scours. We see definite evidence of a terrestrial past when we find bison and mammoth, bison bones and mammoth teeth. Dr. Garrison found an entire bed of these very large sea scallops called placopecten that are dated back to about 40-ish thousand years ago. They are no longer in the area today. And when we find these shell hashes or just mixes of a bunch of different shells, we see a bunch of things that don't really belong in the environment. There's an oyster shell right there. There's one right there. And so we are expecting this mix of past and present. And the oysters I picked out to date, to radiocarbon date, give us some pretty good insights into what this area was in the past. At the site called CCA, we had 2 oysters dated about 7,400 years ago and about 10,000 years ago. And really exciting, at Sagebrush, at one of the JY sites, we had an oyster date to about 42,000 years ago. So these 2 sites not only seem to differ, and to get a real idea of what the actual ages are exposed in the sites, we should do more radiocarbon dating, and I hope we have the money to do it. But what we're seeing here is that CCA, we are looking at a Holocene sort of post-glacial as the seas were rising, shell samples, but potentially much older material at JY Sagebrush. And at JY Sagebrush, I was not able to come on this sampling trip, and I'm very disappointed I did, because when they dropped that robot down, what they saw in the middle of the scour pit was a pile of very large Mercenaria, the hardshell clams. And which is an interesting thing, because we didn't see that at any of the other sites, and that is where we found our oldest shell. We didn't unfortunately come back with any of those Mercenaria, but that is on my to-do list certainly when we go back out this spring, because this was also our site of our oldest dated oyster, well back into the Pleistocene, before in fact the last glacial maximum. So we're looking at repeated transgressions and regressions of the sea here at these sites. Plans for the future.
This is for YouTube, right? Okay. We have to put some humans in the water this spring, and we've already making plans today actually to do that. We're going to go to her clam farm, and you're going to get the clams. We tried with those grabs. You saw them. They just won't get it. I think those clams are hard. I think the darn grab bounces off. But anyway, maybe it wasn't big enough. But we have trainable divers, and they will do what we tell them to do. And if Kelly says bring back clams, they're bringing back clams. We need to get more dirt, more sediments, and that's going to require the ability to penetrate that surface layer and get a little deeper. We don't have to get too far down in. I mean, we're not talking, 10 feet. We're talking, we'd like 10 inches would get us into that and get us an unadulterated sample, which, as Kelly has pointed out, we're trying to avoid the contamination, which seems to have altered our DNA results. And we want to get a pristine sample from, say, 42,000 or 10,000, and we want to look at that DNA without any modern contamination. And we've got to get these really closed sediment cores to do that. We can do that. We're going to do that. And then, of course, we got to go back and do more lab work. That's kind of like paperwork. And again, the divers can do this. They're very patient. They can go through, they can go through and sort through these things. They can get next to the, structures, get into the moat, and I think you'd call it fine work. The ROV is sort of a great hunter, but these are good collectors. So there's room for humans in this experiment as well. And then there's this, which can drop those coring systems and retrieve them better than a small 28-foot boat. So we've been given 1 day of instructional sea time on the Savannah. We're going to bring Kelly's students and some of my students, and we're going to take this vessel out to at least 1 or 2 of the sites, and we're going to collect data. We're going to show the kids how you do marine studies, but we're also going to hopefully recover some information that will be helpful on this project. And there's always too many people to thank, so here's the names that I remembered. And I've left off a name. There's one boat operator who drove the Blanton, and I just went up on his name, and I apologize to him. But next time we do a show, he'll be up there. And this is, like I said, we've got some seriously smart undergraduates up at UGA. And this is 3 of them sitting next to the old professor. And the day is ended. And they're going to River Street, and I'm going to bed. So, so thank you. We're supposed to take questions. I'll go with you first, and then we'll take this lady behind us, okay?
So I don't know enough about this coast, but I know in Florida, beach renourishment is done quite a bit. Has anyone leveraged those boats going out and digging all of that sediment up offshore and worked at those sites for these purposes?
Short answer, no. That's a great idea.
So you mentioned BOEM, and I think they're the ones that would manage a lot of those sites, so, you know.
They've done, on this campus here, they've done a lot of work for BOEM on beach, finding sediment sources for beach renourishment. And their reports give us a lot of information, So no is not the right answer, but they're not expressly doing it for that purpose. But data is data. Yes, ma'am.
I'm just wondering, how deep was your rover when it was?
When he was playing in the Barracuda?
Yeah,
70 feet.
70, that's all.
The continental shelf off Georgia is very shallow. We're operating 20, 30 miles offshore, and we've never seen over 80 feet depths. So you wouldn't snorkel, but it's not good. So it takes a long time to get to the shelf.
You one in the back?
Yeah,
Sure.
I mean, you're trying to find things, you're trying to date things, but the entire shelf sediment system is moving all the time. So even within your scour systems, what you have are modern sediments that have moved around.
Yes and
How do
no.
you actually propose to pin a date on anything?
Well, I'm going to drop into my sedimentary geologist mode. Okay? The sediments below the modern sheet is clastic, and they're not concrete, but they don't move around a lot. And what they do is they resist the current flow very well. So what moves around, you're right, the modern seafloor is moving all the time. I mean, you can, from one year to the next, you can see the difference in just the sand waves. And I've done that. But when we started looking at these scour features, we realized that it reaches a point where, again, it's how much current velocity do you need to pick up a sediment grain? And you reach it at a point off, we don't have those currents that can pick up that sediment that is sort of packed. And that's our target. We're not looking In the sand sheet, we're looking really at, we're trying to look probably at what we would consider to be pack stone. It's not rock, but it's very compacted setting. And if we don't get into that, we've wasted our time. But yes, you're totally right. Things out there change every month. Sir?
That being said, do offshore storms help or hinder you?
We don't go. And it's it's frustrating. We spend more time on the beach than we do on the boat. To deploy the ROV and, okay, for safety reasons, we can't deploy equipment even like that grabber in seas over 3 feet. It's just too damn, excuse me, I almost used the French word there. It's too darn dangerous to have a 50 to 75 pound chunk of iron rolling around and, picking off undergraduates and professors. So, and I think we're constrained. I almost believe that we won't go out in anything that's over 2 feet. And you can count the days that the seas off Georgia are 2 feet. In the summer, it may be, I don't know, 5 days a month, maybe. I don't know. What do you think?
About, yeah.
About that. Grade reef here, he knows. But yeah, but we're patient. We go, we watch the NOAA weather. We look at the marine forecast. We get down on the dock and the weather changes. But that's just the way it is. It's just something you got to put up with. We call her Mother. Yeah, Mother rules. And if you're mean to Mother, she'll be mean to you. Yes.
If your core samples can only be taken at a certain depth, is there a value in taking core samples in areas where the scour has removed the superficial layer of modern sand?
That's where we're really going for the core. And the problem is, and again, this goes back to what I was saying about that clastic sediment. The grabs can't penetrate it. The grabs simply get down there and bounce off. So they can only really pick up the looser sediments, and sometimes that's not what we're looking for. So it's very important that we just get 6 inches into that stuff. Sir?
Is the rover tethered?
Yes, it's tethered. We have 130 meters of tether, so it can run around quite a bit down there. It's pretty reliable. It's pretty reliable. It has its moments, like all people do. It has an attitude. It has a name. It even has a theme song. George Thorogood and the Destroyers, Badge of the Bone. But you need an attitude down there, right? You saw what swam by. Yes. All good? Ask Kelly a question.
I have a quick question for Kelly.
Okay.
What other calcifying organisms or that could you use to have a similar response over time? Maybe another way of asking the question is, why did you choose bivalves for your analysis?
Oh, because I know the most about bivalves. We pull up all sorts of mollusks. So there's bivalves and snails, and I can identify the snails too. We have only found live coral fragments when we accidentally swing it over the boat or swing it over some hard ground. So we have not concentrated on the coral just because we haven't found any dead. We could do forams, and as long as we're doing pollen, we could look for them. We have not. Right? I haven't picked for forams. Yeah.
No, we've not picked before.
Yeah.
Yeah, we're familiar with, pretty good with forams, I think.
Yeah.
Another question.
Yeah.
around your scour nuclei, are there comet tails sometimes on either side because of the, the tidal range that we have?
Yes.
Yep.
Yes. But it seems to be asymmetric. There's always one side that's got more than the other. And I haven't worked that out. I know that you don't want to dive on an ebb tide, right? Or you'll be like that. If you dive on a flood tide, the currents are much gentler, and you don't get shoved around as much. And it's the same thing offshore. You could be 15, 20 miles offshore, and you put the robe in the water, and the next thing the tether's going out. And one reason we have this particular robot, it has 8 thrusters. So power means something down there. So if we hit a current like that, we just boost the power. And the vehicle stays, it can actually hover. Which I guess the best analogy is an underwater drone.
Yes.
What is your archiving process like? Like, what happens once the material comes up and you've identified it? What do you do with it?
What are we
Yeah,
going to do with it? Yeah. Yeah, right now it's all in weight sorted or size sorted plastic bags with some other labeled trays for the mollusks that we're interested in dating. Were you talking about with Dr. Alexander this morning or this afternoon, bringing it down here to archive it?
We were let me say this. Some of the stuff we don't want to archive. We want it to stay in, we want it to be used, and we're going to bring some of the material to Skidaway, and Dr. Alexander is going to do some more analysis and add to his information. But you asked a question about archiving. The National Science Foundation demands that we digitally archive everything, and that's, again, a lot of busy work that we have to do yet. We try to do it while we're working, but it only gets as far as an Excel sheet. And we've got a lot of Excel sheets which have to be compiled, they have to be entered into this database, and it has to be public. So people who want to access our data, NSF demands that we make it public. So we've got a lot of busy work this summer, I think, where it was, get the coffee, turn the workstation on, and go by it.
How long is the grant for?
Sure.
How long is the grant for?
We turn into a pumpkin in July. But now, let me say this, because we were funded, and not just us, just because we were funded in 2020, the NSF gave everyone that was funded in 2020 an extra year. And thankfully, they did. We could not have done this project in 20 through 21. It would have been impossible. So we caught up in 22, and we're just about even now. So I think we feel comfortable with where we are. Yes.
You mentioned that the DNA testing was rather disappointing because it seemed wrong. What were you hoping to see?
So I was expecting to see, given our sampling techniques, it is truly impossible to keep modern DNA out of that sample. I was expecting to see a mix of at least marine terrestrial.
Yeah.
There was no marine DNA on any of the samples, including the one that I gave them. Will probably keep worm analysis too. So I'm truly not sure what's going on there. What it looked like when we got the results back, I looked at it and I said, if I had swabbed the bottom of my shoe, this would that would have been the environmental DNA. It was lawn grasses, liverworts, a freshwater paramecium. So I was expecting to at least see some marine DNA, given that the sediment came from the bottom of the ocean, and we didn't.
So are you going to give up?
No, we're not going to give up. We're going to try to improve our
Get a
sample
different
techniques and maybe-
contractor.
Yeah, and maybe change labs, yeah.
Oh, thank you.
Yeah.
Now, I have a question. Do you have a lab?
Dr. Mark Fisher.
What is it?
Mark Fisher here on campus.
All right.
We're talking, thank you. This is helpful, because we're not ignorant of DNA, we've not had used it very much. And environmental DNA is really sort of the new kid on the block. And it's really hot, it's not horribly expensive, and I've seen really extraordinary results, but we haven't seen it. So we've got to do better and hopefully, again, find another lab. Yes.
You seem like you're in the kind of in the middle of the data collection right now. You folks obviously have done this and have a lot of experience. Based on what you're seeing, are there any kind of results, or do you ever do you go, oh, in a year, directionally, we're hoping it's going to validate that this is going to be the end result, or the kind of key conclusions?
This was a sort of a, and please correct me if I'm wrong, this was sort of a method exploratory grant. Is it worth looking in these scour nuclei?
Right.
And I think we can say yes to that question with the results that we have. It is worth looking in these for, at the very least, a concentration of heavy stuff that may be bones, maybe projectile points, maybe very old clams in the bottom of these scour nuclei. There will be a lot of still moving pieces and pieces that we wish we had more information on by the end of July, 100%. Yes.
So, I mean, you're looking at scour nuclei, but they are placed randomly with respect to the seafloor. And if you think about what the modern analogs are, what you should be looking at are river bends, bar deposits, things like that. How are you making any effort to identify those paleo locations and focus on them?
Yes.
Yes.
And one of the things I was commenting on when we started looking at our data, plus certainly the Bowen data, the amount of paleo channels, small and large out there, is striking. And when going in to the proposal, we wanted to cite, DNR puts these structures where they want to. We want when we select them, we have been selecting areas where we think they're going to be near channels or as close to these estuarine features as we can get. We've concentrated primarily on ocelot. There's two reasons. A, it's closer to Skidaway, and it's not as long a boat ride. And two, there's a lot of paleo channels off ocelot. And I think we have, at least in one instance, landed and taken samples. We've got some really fine sediments that don't look like medium sand. And it's puzzling to us, but we think we're in an environment that may be related to, say, an estuarine feature or perhaps a channel feature. But there's a whole lot, that's just an assumption, we got to do more work. But yes, we really want to land on those features.
Well, thank you very much for coming, everyone. If you're not on our email list, please sign up and we'll make sure you get all the notices of upcoming events.